Welcome to The Explainer. Today, we're diving straight into the absolute bedrock of the digital world. For over half a century, the entire tech industry has been propelled by this one seemingly unbreakable golden rule. I mean, it's literally the reason why that smartphone in your pocket crushes the computers that put humanity on the moon. But we're about to look at a massive plot twist. That golden rule, it's breaking. And what's rising from the ashes is fundamentally reshaping the future of computing.
He brings up a totally wild question, right? Are we actually reaching the absolute limits of technology? Think about it. If the foundational law that's governed our progress for decades is finally hitting a brick wall, what happens next? Do we just stop innovating? Well, as we're going to see, humanity isn't hitting a dead end at all. Actually, scratch that. We're basically being forced to tear up the rulebook and start completely fresh.
So let's get into it. Section 1, what exactly is Moore's Law? To really grasp why this rule is dying, we kind of need to understand what it was in the first place. And the crazy thing is, it wasn't even a law of physics. It was just an observation, a hypothesis from Intel co-founder Gordon Moore. Early on, he noticed that engineers could reliably double the number of transistors, those tiny little electronic switches on a microchip, roughly every 18 months. But here's the thing, it quickly mutated into a self-fulfilling prophecy. It became the undisputed target. Heavyweights like Intel and AMD literally built their entire business models around hitting this exact metric. And look at how incredibly accurate this target was. Take this timeline from the late 90s. When Intel dropped the Pentium 2, it had about 7.5 million transistors. Fast forward 18 months, Moore's Law says they should hit 15 million. 36 months, 30 million. By month 42, the math projected around 37.8 million. So what actually happened? Well, 42 months later, Intel rolled out the Pentium 4, and it packed a mind-blowing 42 million transistors. No joke, the industry didn't just meet Moore's Law, they totally obliterated it. They were actually underestimating their own massive growth.
Which brings us to Section 2, physical and economic limits.
Okay. Here's where things get tense. You simply cannot shrink physical objects down infinitely without eventually hitting a wall. As companies tried to cram more and more transistors onto a single chip, they had to make them unbelievably small. We're talking down to the atomic level. And when things get that microscopic, the normal rules of physics just kind of stop working. We start fighting quantum mechanics. Electrons actually start leaking across barriers, causing what engineers call quantum parasite effects. You get unwanted interference, chips getting insanely hot, and electrons basically acting like rebellious teenagers that are impossible to control.
But physics wasn't the only headache. We also hit a massive economic barrier. This introduces Moore's second law, an observation coined by early Intel investor Arthur Rock. He noticed something terrifying. Sure, chips were getting smaller and faster, but the ultra-advanced factories required to build them, they were getting unsustainably expensive. Basically, the cost of the manufacturing equipment was doubling every 4 years.
Let's put that into perspective, because the sheer scale of these numbers is wild. Back in 1966, a state-of-the-art semiconductor factory would set you back about $14 million. Jump to 1996, and that exact same class of cutting-edge facility, $1 billion. And as the tech got even more ridiculously complex, just to combat those quantum physics issues, the projected cost for a factory in 2005 just absolutely skyrocketed.
$10 billion. This is the ultimate record scratch moment for the tech industry right here. Because at $10 billion for a factory, the foundational promise of Moore's Law, the idea that computing inherently gets faster and cheaper, it totally broke. The investment needed just to pull off the next generation of tech grew exponentially, meaning the actual cost per transistor started going up. The traditional path wasn't just physically exhausted, it was financially exhausted too.
And that leads us to Section 3, the AI problem.
This slowdown in computing literally couldn't have come at a worse time, because the software world was trying to pull off a revolution. People tend to forget, AI isn't some brand new concept. In fact, neural network research hit brutal walls twice, periods scientists grimly refer to as AI winters. The first one, back in the 70s and 80s, was simply a lack of cash for the crazy expensive computers they needed. The second winter hit when researchers realized their algorithms just couldn't scale. They totally lacked the raw compute power to make the math work. So the big takeaway here is that artificial intelligence needs two fundamental things to actually survive and grow: massive amounts of data to learn from, and immense computing power to process all that data. Now, the internet eventually solved the data problem, right?
But those traditional processors, the CPUs, stuck behind Moore's failing law, they were totally the wrong tool for the heavy lifting AI required. They were way too slow and way, way too expensive.
Enter Section 4, CPU versus GPU.
And here is the big plot twist. We didn't just need better processors. We needed a completely different way to process information. Let's break this down. A CPU, your central processing unit, uses sequential processing. It does one task at a time, super fast, strictly in order. A GPU, the graphics processing unit, uses parallel processing. It does thousands of tasks at the exact same time. Think of it like this. A CPU is like having 4 brilliant college professors solving incredibly complex equations one by one. A GPU, it's like having an army of 10,000 elementary schoolers doing simple math all at the exact same moment. And for AI, you don't need the professors. You need the army.
Now, this required a totally new programming paradigm called stream processing. Instead of waiting in a single file line, the host CPU grabs a massive block of data and just throws it over to the GPU. The GPU then applies a kernel, basically a function, across thousands of parallel streams all at once. Finally, the host extracts the massive output. This completely sidestepped those old sequential bottlenecks that were killing Moore's law.
But wait, originally, GPUs were literally just for playing video games and rendering 3D graphics. The massive game changer happened in 2006 when NVIDIA dropped CUDA. This was a revolutionary software architecture that allowed developers to write standard code and run it directly on those thousands of GPU cores. Almost overnight, the GPU wasn't just for gaming. It was unlocked for general-purpose computing. This single move basically rescued the entire tech industry, giving AI the cheap, scalable power it had been starving for.
Moving on to Section 5, the new era of computing. This breakthrough completely shifted the ground beneath our feet. We moved away from Gordon Moore's traditional computing model. To really capture the vibe of this new era, listen to this quote from Bill Daly, NVIDIA's chief scientist. He said, "We can multiply transistors in cores, making each core work slightly slower but more efficiently, more than tripling performance with the same consumption. That is huge. The new game isn't about forcing one single core to run at physically impossible speeds. It's all about parallel efficiency." And leaning into that parallel efficiency is paying off big time. Modern architectures like NVIDIA's Blackwell GPUs are literally 20 times more energy efficient than traditional CPUs for AI workloads. To put that into perspective, if the entire world shifted over to these accelerated systems, we'd save nearly 30 trillion watt-hours of energy a year. That's insane. We aren't just computing faster anymore. We are computing vastly smarter. When we zoom out and look at this monumental shift, the contrast is super clear. In the traditional tech era, we relied on sequential CPUs for high-speed single tasks. But today, in our accelerated era, it's all about parallel GPUs. And the defining capability of this new era? It's the ability to train massively complex foundation models, like ChatGPT-4, which flexes a staggering 1.76 trillion parameters. Doing that under the old rules of Moore's law, absolutely physically and economically impossible. Which brings us to our final thought for this explainer. We started out asking if we were reaching the limits of technology. Well, it turns out the physical and economic death of the old Moore's law wasn't a dead end at all. It was an invitation to invent a completely new way to process the world. So I'll leave you with this. If the old Moore's law is dead, are we currently just writing the rules for a brand new one? Thanks for joining me on this deep dive, and keep your eyes on how this accelerated future unfolds.